In the last class, we were discussing about, or we were revising the topic of normalization. So we have seen that when you are trying to develop a database for a given application, multiple designs are possible. For the same problem, uh, people can come up with different designs. So we can rate these designs, and we can say that some designs are good and some designs are not up to the mark, or there are some problems with that. So we have seen the parameter on which one of the parameters on which we can compare the designs is actually the level of duplication or level of data replication present in the designs. So as some of you have rightly pointed out, if there is a lot of replication or if there is huge amount of data duplication, there can be problems during uh, data insertion, deletion, searching, etc. Okay, or lot of anomalies may come when you are having multiple copies of the same piece of data. All right. So if you have many copies, you also have pointed out that there can be multiple answers for the same query, because all copies of the data may not be having the same value all the time. So it may happen that for the same question you get two different answers from two different copies. Maybe the data or the query may be referring on another copy of the data, so you may get a different answer. For example, the department may say that your CGPA is 8.5. Maybe the placement department may say that your CGPA is only 8.2. Such things can be given that if you have only one copy of a data at one place of time, at one place. All right. So this is actually the intention behind the normalization theory. Normalization is actually a technique by which one will try to remove the redundancy present in the database design. All right. So we have seen that there are different normal forms available, from first normal form to fifth normal form. And the higher you go in the normal form, uh, lower will be the redundancy. Or in other words, we have seen that by removing the redundancy, the database designs normal form will be higher. Okay, so we have seen that there is a condition, or there are conditions for a relation or a set of relations to be in a normal form, in a particular normal form. And if those conditions are satisfied, we can say that the relation is in that specific normal. So these slides are actually from the textbook on database system concepts by Shilbert, Schwartz, Korth, and Sudarshan. So chapter 7 of all right. So we have seen that uh, by looking at a table, we will not be able to say in which normal form it is. So you require some additional information. So what is that additional information that we require, Abhinav?
Yes, sir. Please repeat the question, sir.
What is additional information?
Uh, Sir, attribute should be atomic.
Attribute belongs to?
Should be atomic, sir.
No, no. What I'm saying is, by looking at a database design or on the schema, one will not be able to comment on the level of redundancy present in the table. So how do you, what additional information you require in addition to the schema?
Functional dependencies, sir.
Okay. So in general, I can say that you require the meaning of the individual attributes, or you require the meaning of the data. So like when you talk about a program, you have both syntax and semantics, and these database designs are also having syntax and semantics. So the semantics of the database or semantics of the data is actually expressed in terms of the dependencies. I mean, in terms of many different things, and one commonly accepted form is actually the dependency. So there is functional dependency, FD, there is multi-value dependency, MVD, and there is another form of dependency which is called join dependency. So there are different forms of dependency. Okay, so these are all ways by which we can express the meaning of the data, or how the different columns of a relation are interconnected, or how they are dependent. That can be expressed using this functional dependency or dependency concept. Okay, and we have seen that if all the underlying domains or the values taken for the different columns are atomic, that means if they cannot be broken further, you call that the relation is in first normal form. All right. So the condition for a relation to be in first normal form is that all the individual values or all the columns or all the fields should have atomic values. Atomic values means those values cannot be divided, or should not have further components. So can you give an example for a atomic and non-atomic field, Agnijit?
Yes, sir.
Can you give an example for a non-atomic field?
Address.
Address, how it is
Yeah.
becoming
So
non-atomic?
it includes the country, the state, the district.
All right. So if it is having further components like address, house number, street
Yeah.
number, email ID, etc., then it is going to be a it is not atomic. All right. Okay. So, and by definition of a relation, set theoretic relation, actually only atomic values are allowed in a relation. All right. Okay. Now, okay, here another example is given regarding normal atomic values. All right. Mm. Yeah, so we are coming to the concept of functional dependencies now. So we have seen that functional dependencies are actually a mechanism, or it is a notation which is used for expressing the semantics or the relationship between different columns of a particular relation. All right. So when you are, the technique that is normally adopted in normalization is to decompose a table into smaller tables. All right. Decomposing a table into smaller tables. So when you are decomposing a table into smaller tables, one thing that you have to remember is that no data should be lost. Not only that, and none of the functional dependencies should be lost. No data should be lost, and no functional dependencies should also be lost. That means if none of the functional dependencies present in the table are lost, it is actually called a dependency preserving decomposition. or it is also called a lossless join decomposition. So a lossless join decomposition means no data should be lost. So when you take the join of the tables, the new tables, you will be getting the original table back. And second thing is that none of the functional dependencies should be lost. Okay? So lossless join decomposition means no data is lost or no functional dependency is lost because of a because of the decomposition of a table. So there are different types of functional dependencies, different types of dependencies. One is FD, functional dependencies, other one is multi-value dependency, and you have JD, join dependencies, and many other forms of dependency. So let us see what is actually functional dependencies. So the functional dependencies are actually constraints on the set of legal relations. Okay, functional dependencies are actually some constraints set on legal relations or legal tuples in a relation. So it requires that the value of certain set of attribute determines uniquely the value of another set of attributes. So a functional dependency is a generalization of the notion of a key, which we have seen in the last class. Okay, we have seen regarding primary key, secondary key, candidate key, super key, etc. in the last class. So these functional dependencies is a generalization of the notion of keys in a table. So Ajwad, can you give an example for the second bullet? That is, FD is something where attributes, a certain set of attribute determines uniquely the value of another set of attributes. So can you give any example for that from any application? Ajwad,
Sir, yeah.
yeah. Any example? Say from the student table. Yeah, Arka Jodi. Any
Yeah, hello, sir.
yeah.
Yeah, and like a student ID can give the respective name or maybe the address of the student.
Okay, so when you specify the student ID or the roll number, you get the name because, or you can say you get the rest of the tuple. Okay, so because student ID is going to be unique or the roll number is going to be unique for every student. So I can say that roll number functionally depends the student name. All right. Now, Avinash Kumar, can we say that when say every student is having a unique roll number, can I say that from the name you can say the roll number or the name determines the or name uniquely identifies the roll number? Can we say like that, Avinash?
No, sir, we cannot say that.
Why?
It may be the case that two are having the different roll numbers, but they can maybe having the same name. Like suppose if there are two students of same name Avinash Kumar in the same class, then it will
Yeah,
although they will
there
be
can
having different.
be two Avinash Kumars and they will definitely have two different roll numbers. So from your name, we will not be able to say what is his roll number. So that means we can say the roll number functionally determines the name, but we cannot say that name determines the roll number. That can be the case. There can be another case also. For example, roll number determines mobile number, and in that case, can we say that mobile number determines the roll number? Vishal. Suppose every student is having a unique mobile number. Then
Yes, sir.
can we say that roll number determines mobile number?
I think, sir, no, sir, because a particular student can have more than one mobile number at the same time.
But in the table, you will have only one mobile number entered, isn't it?
Sir, then we can select it.
Then Vishal.
Sir, then we can use it for identifying it.
Okay. For that, I have to tell whether two students can have the same mobile number. Maybe the mobile
Yes.
number is shared by different students. If that is not the case, so every student is having a unique mobile number, then I can say that roll number determines mobile number. And can we say the mobile number determines the roll number, Chedana?
Sir, yes, sir. Mobile number can determine roll number if mobile number is unique.
Unique. If it is unique, we can say that mobile number can determine the roll number. All right. So in that case, both ways it is true. Roll number determines mobile number determines roll number. That may not be always the case. All right. So a functional dependency is actually a generalization of the concept of a key. All right. Or we can say that from this concept of FD, we can define what is actually a key. So here it is a formal definition of these functional dependencies. Let R be a relation schema and alpha is a subset of R and beta is a subset of R, a proper subset of R. Then we say that alpha determines beta or beta is functionally dependent on alpha if R in R, if and only if for any legal relation R, small r, which is a tuple of capital R, whenever any two tuples T1 and T2 of R agree on the attributes alpha, they also agree on the attribute beta. That means whenever the roll number are the same, then the name is also going to be the same. Or whenever the roll numbers of two different tuples are going to be the same value, you can say that their CGPA is also going to be the same because roll number determines CGPA or roll number determines the name or roll number determines the email ID, right? So our functional dependency alpha determines beta. This one alpha determines beta holds on a relation R if and only if for any legal relation R of capital R, whenever any two tuples T1 and T2 of R agree on the attributes of alpha, they also agree on the attributes of beta. That is, if T1 alpha is equal to T2 alpha, it implies that T1 beta is also equal to T2 beta. All right. So an example is given here. So here you can see that A determines B is it true? And A determines B does not hold because if this is column A, you can see that 4 is the 4 is paired with 1, here 5 is paired with 1. So A determines B is not correct here. But B determines A is correct. Because for 4 there is only one value, for 5 there is only one value, for 7 there is only one value. So this is an example where A determines B is not correct, but B determines A is correct. Is found to be correct. So functional dependencies going further, we can see that there is something called full functional dependency and partial functional dependency. All right. So if K is a super key of a relation schema R, it is called a super key if and only if K determines R. That means it can determine the whole relation schema. If K is a candidate key for R, if and only if K determines R, and for no proper subset of K, or for no proper subset alpha of K can determine R. Okay, so if alpha determines R, and if no proper subset of alpha can determine R, then we say that the dependency of R on alpha is full. Full functional dependency means, suppose you have an FT, X determines Y, that is called full functional dependency if Y is dependent on X and not on any subset of X. Okay, in that case, the functional dependency X determines Y is said to be a full functional dependency. So functional dependencies allow us to express constraints that cannot be expressed using super keys. All right, an example is given here. So please go through the example. So here what is underlined is actually the key. You have customer ID, loan number, and you have an amount as another attribute which is determined by this key. Now the question is customer ID, loan number determines amount. Is it going to be a full functional dependency or partial functional dependency? Demira? Mira
Yes, sir.
Tarun?
Yes, sir.
Is it partial or full? Customer ID, loan number determines the amount.
I think it is full, sir. With loan number, we can uniquely identify amount. So it's partial. Sorry. Without customer ID, we can directly determine amount. Sorry.
By loan number itself, you will be able to identify the amount. So it is a partial functional dependency. So
Yes.
a subset of customer ID, loan number, that is a loan number alone, is able to identify the amount. So it is actually a partial functional dependency. Correct. So use of functional dependencies. Functional dependencies can be used to test relations to see if they are legal under a given set of FDs, and if a relation R is legal under a set of functional dependencies, we say that R satisfies F. Okay. So in addition to a relation schema, you also get a set of functional dependencies. So this is what I was referring to earlier as semantics of data. So semantics of data corresponds to, or it is really implemented as a set of functional dependencies. All right. So we say that F holds, if a relation R is legal under a set of functional dependencies, we say that R satisfies F, the set of functional dependencies. So in order to convey the meaning of a relation, we should give the schema of the relation and also the set F, that is a set of our functional dependencies. All right. So we say that F holds on R if all legal relations on R satisfy the set of functional dependencies of a specific instance of a relation schema may satisfy a functional dependency even if the functional dependency does not hold on illegal or on legal instances. For example, a specific instance of loan may by chance satisfy the condition amount determines customer name, but That may not be always true. All right. Any questions on this? So there is legal and illegal tuples, or there are legal instances of a relation schema, and that is actually decided by the functional dependency. So from the given set of functional dependencies, we can derive many additional functional dependencies. So they are actually called derived functional dependencies. All right. So you have functional dependencies and derived functional dependencies, or closure set of functional dependencies. So you can see that a functional dependency is trivial if it's satisfied by all instances of a relation. So here, customer name, loan number determines customer name, and it implies that customer name determines customer name. It is actually a functional dependency which is a subset of the first one. So it is actually called a trivial functional dependency. A dependency of the form X determines X or Y determines Y is actually called a trivial functional dependency. Okay. So trivial functional dependency means they are functional dependencies of the form X determines X or Y determines Y. All right. So non-trivial means other function dependencies other than trivial. That means X determines Y, and X is actually not, I mean, Y is not a subset of X, then you call it as non-trivial function dependency. Okay. Now closure set of functional dependencies, F closure. Given a set of functional dependencies F, there are certain other functional dependencies that are logically implied by the functional dependencies present in F. For example, if A determines B and B determines C, then we can infer that A determines C. This is actually the transitivity rule. That means B is functionally dependent on C, B is functionally dependent on A, and C is functionally dependent on B. This implies that C is functionally dependent on A. The set of all functional dependencies logically implied by F is the closure of F. So we denote the closure of F by F closure. So this is actually the symbol for F closure, the closure set of all functional dependencies. So F closure is actually a superset of F. By applying certain rules like transitivity, like mentioned here, A determines B, B determines C, means A implies A determines C. Like that, you have many rules. And using those rules, you will be able to derive many additional dependencies. And those derived dependencies, along with the direct dependencies, is actually called the closure set of functional dependencies, F closure. Okay. Any questions on this? Any questions? Divyanshu? Divyanshu, any, do you have any? Any questions, Divyanshu?
No, sir, no question, sir.
Okay.
No question, sir.
Oh. Okay, so we will go. So we are going to see the normalization concept, which are actually defined based on the concept of functional dependencies. The normal forms are actually certain logical conditions in which a particular relation can be in, and they are actually defined in terms of the concept in or by making use of functional dependency concept. So the normal forms up to BCNF are actually defined based on FT, and the normalized normal form 4NF is actually defined on the concept of multivariate dependency, and the normal form 5NF is actually defined based on a particular form of dependency which is called joint dependency. So first let us see BCNF, Boise code normal form, which is defined based on the concept of functional dependency. So please go through the points mentioned in this slide. I will explain this. First you read the slide. So there will be certain questions based around these slides. So please read carefully. Sunita, from this slide, can you just state the condition for a relation to be in BCNF? Sunita? Sunita absent. Satya?
Yes, sir.
Yeah. Can you just tell the condition for a relation to be in BCNF by reading the points in this slide?
In a given functional dependency, sir, alpha on P, it has to be either trivial or alpha has to be a super key for the given
Should
relation.
be either trivial or
A super key, sir.
super key. Okay. So can you just say more on that? What exactly it means?
That means it has to either uniquely identify all the attributes of the relation, or it has, or the beta of the functional dependency should be a subset of the alpha, sir.
Okay. So Megha, can you add anything more to what Satya has told regarding the condition for a relation to be in BCN?
Yes, sir, that should be in 3NF also.
That is not mentioned here.
Yeah. Table should be in 3NF and every functional dependency X to Y, X is the super key of the table.
Okay. Yeah, that is what I'm saying. The condition 3NF condition is not being stated here. So here the point is that if there is a functional dependency of the form X determines Y in a table, then X should be the key of the table. If that is the case, then you say the relation is in BCN, right? If for every functional dependency of the form X determines Y, if X is coming as a key of the relation, then you call it as the relation you describe it is satisfying the condition for BCNF. All right. For every functional dependency of the form X determines Y, X should be the key of the relation or key of the table. All right. So if there is a functional dependency, X determines Y, X should be the key of the table. Otherwise, you have to split the table in such a way that X becomes the key of the table. If that is satisfied, then we say that the relation is in BCNF. So BCNF is more powerful than other normal forms like 3NF, and it is especially useful in the context where you have overlapping candidate keys. Okay? When you have no choice, but you have different there is overlapping among the different keys of the relation, then you call it, or then you may find that BCNF is much useful. All right. Now let us see more about BCNF. So decomposing a schema or a relation into BCNF. Suppose we have a relational schema R and a non-trivial functional dependency of the form alpha determines beta, then which is causing a violation of BCNF. Then what we have to do is we have to split the table in such a way that alpha, you form a first table, split the table into two with alpha and beta attributes or fields coming as one table, and all attributes in R other than beta coming as another relation. So this is actually the thumb rule that we are going to apply. Divide a table into two, and in such a way that for every functional dependency of the form alpha determines beta, alpha beta becomes a table, and the other one that means the relation minus alpha plus beta. Alpha should be removed and beta should be retained. So beta should be removed, but you will have alpha retained. So that will be the decomposition. Okay, you can just see that here you have in the you have a relay FD where you have alpha is representing lone number and beta is representing amount, and alpha lone number determines amount. So you make, decompose in such a way that alpha union beta becomes one table, that is roll number amount is becoming one table, and the other one customer ID plus loan number, that is without beta or without the amount, is forming another table. So here the idea is, if you have a functional dependency of the form alpha determines beta, make alpha beta as one table in order to satisfy BCNF, and R minus beta and rest of the attributes other than beta will form the second table. If that is the case, we can see that the first one alpha beta is going to be in BCNF. The second one depends upon many other factors. So BCNF and dependency preservation, the constraints including functional dependencies are costly to check in practice unless they pertain to one relation. If the FDs are not pertaining to a single relation, it is very difficult to check. It is sufficient to test only those dependencies on each individual relation of a decomposition in order to ensure that all functional dependencies are holding, and that then the decomposition is dependency preserving. So the decomposition should be preserved in a table as well as when you split the table, then also the FT should be satisfied or it should be preserved. Because it is not always possible to achieve both BCNF and dependency preservation, we consider a weak normal form, which is actually called third normal or 3N. So the last bullet is very important when we go for 3N. In situations where you are not able to achieve dependency preservation and BCNF condition satisfaction, then you may go for a weaker version of the normalization, which is actually called third normal form. Right? So that is actually 3NF. So we'll see 3NF in the next class. So before that, if you have any questions, you can ask now. Are there any questions?